Hi, I'm Patrick. I'm an artificial intelligence engineer, and today I'm going to show you how to make a neural network from scratch. So neural networks kind of flip computer science on their head in a certain way. So normally in computer science, we have input data and we have some sort of algorithm, and that algorithm turns our input data into useful output data. Neural networks kind of rearrange the objects a bit. So we have input data and we have output data, and the neural network tries to convert the input data consistently into the output data so it discovers the algorithm or the program that converts the data. That's kind of interesting, and that's the conceptual bit behind neural networks, the really interesting part. So what is a neural network functionally? What are its parts and what does it look like? You may have seen them before. They look kind of like this, and they're quite beautiful, I think. There's all these like little nodes and wires connecting them. They look like a living organism if you look at them just right. So there are two basic things you do with a neural network. You perform forward pass and backwards pass, or you forward propagate and you back propagate. Sounds complicated, but here's effectively what it means. Let's say we have a couple of digits that we think are going to tell us whether or not we buy a stock or not. And the digits are 0.1, 0.2, and 0.3. Let's plug those into our input nodes over here at the start of the network. Then we forward propagate that across the network. We don't need to think too technically about what forward propagating means for now, but think of it like the network's thinking about the data. It's guessing, and it's guessing based upon random weights, as they're called, which are assigned to individual nodes in the network. So at the beginning, these weights are random because the network doesn't really know about the problem. It's never encountered examples of the problem before, so it's just guessing. So it takes a wild guess, and we propagate our data through the network until we get to a result. Buy the stock or don't buy the stock. Now, initially, if it's just a binary choice like buy or don't buy, there's a 50% chance it's going to get it right. If it gets it right, well done. Let's try again. Forward propagate, that time it got it wrong. What does it do when it gets something wrong? Well, this is an informative example. It needs to change its ways, do something different. But how does it do that? It does it using something called backpropagation, where it will take the fact that it's made a mistake and use that to update the weights of the individual nodes that compose the network. Now, you don't need to know a lot about the computation involved yet, but hopefully that makes a lot of intuitive sense. The network, when it makes a mistake, knows it has to change. Like if you try to make cookies and you burn them, you're going to hopefully try again, be an amateur baker and all, but you're going to do it a bit differently. Maybe you're going to set a better timer. You're going to update your procedure. This is the same sort of thing the network is doing. It's updating based upon the signal it receives from its results, the success or the failure. Now, this is a contrived example. The network didn't have to resolve to a binary outcome. It could have been a class of object, or a real number, or a vector of numbers. Networks are quite flexible in terms of the outcomes they can produce if you design the architecture of the network correctly. And this is where we really get into the meat of what it means to make a neural network. So let's dive into some code and produce your first neural network. So first of all, if you're used to Python, this is going to make a lot of sense. But if not, I'm going to try to provide an intuitive sense of what every block of code does. That way you can follow along to get an intuition of what we're doing if you have no coding experience. Or if you have a lot, this should be pretty transparent and you might be able to replicate and change it yourself on your own time. I'm using what's called a Google Colab notebook, and you can open this using almost any web browser as far as I can tell. The link to get to this notebook is in the video description. If you just pop down there and take a look, you can open this up in your own browser and build your own neural network in just a couple of minutes. So let's take a look. Okay, so now we're inside Google Colab. This is going to allow us to use Google's cloud resources to run our code. So you don't have to worry about whether your machine has like a high-end GPU or anything. So initially, our first block of code here is going to import some useful libraries. This includes Tensorflow, Matplotlib, and NumPy. Now, if you've done a lot of work in Python before, probably Matplotlib and NumPy are pretty familiar with them. Effectively, these are mathematical or visualization libraries that allow us to do things with vectors and with tensors. They're just really useful. One library you should keep in mind, and maybe you don't have a lot of experience with, is Tensorflow. This is a open source platform by Google for doing deep learning. In particular, we're going to use a subsection of TensorFlow called Keras, which is going to make it really intuitive to craft those neural architectures like we saw at the beginning of the video. So to keep things simple, we're going to create our own data. What do we mean by this? Well, we're going to use a mathematical function, and we're going to take input numbers and turn them into output numbers. This might not be very exciting, but I don't want to make it too complicated for your first try at a neural network to use something like a 100 gigabyte data set. This might be a bit intimidating. So we're going to produce all of our data inside the code itself. But functionally, you can think of it the same. Like if I have an input image and I then categorize that as a particular kind of animal, that's a function. We're taking an input image and we're producing an output, which is the class of image that it is, whether it contains a cat or a dog or a giraffe or a monkey. So hopefully you can see why this is similar philosophically to almost any approach you might use a neural network for. So here we have a very basic mathematical equation. If that notation is confusing because you aren't used to writing your equations in code, it looks like this. Pretty basic. You've seen stuff like this before. We take a bunch of random numbers and we pump through that function and we get an output vector. Now we have this input and output data set, and we want to use deep learning to create an approximation of what that function was. So let's see how we're going to do that. We define our neural architecture. This is the most enjoyable part of building deep learning models because right now at least, it's part art, part science, and there's a whole lot of trial and error involved. You have to work hard to gain intuition for what the correct approach is. There's tons of things that go into crafting a neural architecture, but here we'll keep it pretty simple. Okay, so let's take a look at the neural architecture we've decided to use to solve this problem. We're using a dense, fully connected network. This is also called a multi-layer perceptron, or MLP. It's one of the oldest kinds of deep neural networks, and it goes back many decades. Now, today we have much more powerful hardware, so we're able to harness them in new ways. Even a relatively simple architecture like this has many, many applications and goes way beyond the simple ability to approximate a function. Ours has 5 layers, and if you look here, you see the dimensionality, which is a fancy way of saying the number of nodes in each layer. We start out with 64, we expand our network to 128, we move on to another layer of 128, we go back to 64, and finally we resolve down to that one network node, which corresponds to our guess about the output of the function. Down here you'll see, after this model.compile call, that we have loss, which is assigned to mean squared error, an optimizer called Atom. Without going into too much detail, the loss function, which here is mean squared error, gives the network a sense of how well it's doing. Once it creates a prediction, it needs to know how close it was. Was it very close? It needs to update those nodes in the network just a little bit, or was it majorly off and needs to refactor things quite a bit? Atom is a lovely name for a fantastic optimizer. This handles how those nodes get updated after the model makes a mistake. We'll go into those more into detail more about those in the future, but for now, know that Atom is a very good optimizer and can be used across many, many different kinds of neural networks. After that, we build the model, we output a summary, and we output the results. So let's take a look at how our model does approximating this function. Okay, so let's take a look at how our network operates. Let's go up here and run the network. We see here that it's training. It's running across batches and epochs. Without going into too much detail, batches are the number of concurrent examples that we push through the network, and the number of times we do that corresponds to epochs. Now, batch size matters. It's not an arbitrary thing, and so do the number of epochs. If you aren't careful and you train your network too thoroughly, the network can often just memorize the data, and instead of learning about the general rules that generate the outcome, it'll just memorize which inputs correspond to which outputs, which is called overfitting. That's generally bad. Okay, so our model quickly finished training. The loss here corresponds to how well the network is doing. So when your network is training properly, you expect the loss to descend. Here we start with a very high loss of 1,715, and it goes down and down until we get all the way to 0.008. That's a pretty good loss. We're gonna go with that. So what we have here is a set of outputs that I've programmed. We take the first 3 numbers in our input vector, and we compute the result using our function. We know that that's right. That's our ground truth. What we have here is the result is 74, 123, 192, and some change for each of them. Then we take our model, the one we just trained, and we ask it to predict or calculate the resulting numbers. So what we have here are a very similar set of numbers. Now they're not quite the same, and this is an important thing to note. Neural networks are not analytic solutions. They're not going to give you the exact right answer a lot of the time. Sometimes they will. If, for example, if you're doing a binary classification, oftentimes you'll get the precise answer a lot of the time. But it's important to note that the neural network, when it's trained on a function, it is approximating that function. It has an idea of the function. But does the function actually exist inside the neural network? That's a very deep philosophical question, and we're not going to go into it here. But just be prepared for your results to not always be perfect. This is where engineering comes in. How do you address the problem of approximation? What constitutes close enough for your particular application? And do you have enough data and a powerful enough network to get you to that good enough threshold? These are all considerations that a good engineer takes into account when they think about applying a neural network to solve a problem. Now that we've done all that, let's create a graph to show how well our network is doing. Down here we can see that I've created a graph, or you've created a graph if you've run this code, that corresponds to our initial function, the one that we defined analytically and explicitly at the top of the code, and our approximated neural network function. And we see here that they're tracking along almost perfectly together, where the thin blue line is the actual function and the thicker blue line is the approximated function. They're tracking in lockstep with each other. This is a great indicator that we're on the right track, and I would say this model is ready for deployment. Okay, not really. There's a lot we need to do before a neural network is ready to be deployed. You have to be very careful with that. But I'd say we're on the right track. So we've done it. We've created a neural network that subsumes the role of the initial function that we defined at the top of this code. What have we really learned here? We've learned that neural networks perform a different kind of task than a lot of normal software. In most software that you're familiar with, you have input data, you have some sort of program that operates on the input data, and then you have an output. But here we've created input data, output data, and we've created the bridge between them. That's what makes neural networks and deep learning so different than other kinds of software. It's a natural extension of older traditional machine learning techniques. And it takes those capabilities and generalizes them to a whole new areas, whole new kinds of problems. I hope you see, at least philosophically, the power of deep learning and its ability to really revolutionize how we write software. Now, I should note before we go that this is an example of supervised learning, where we explicitly have the input and the output data. But there are other kinds of neural networks that deal with scenarios that are much more interesting in nature, called unsupervised neural networks, or semi-supervised, or reinforcement learning. We're going to go into more detail on those in the future. Just rest assured that things can get pretty funky pretty quickly. But for now, at least you have an understanding of the core kind of capability that a neural network provides. And that's pretty cool. And you did it all with 5 minutes of your time and a web browser. Now you can go tell people that today you trained a deep neural network. Congratulations.